I would like to explain my capstone project, which is Robotic Assistant for Mobility Impaired Patient, in short, RAM. My name is Puen and my team members are Alice, Farah, and Hannah. Before we start, I would like to give you the background of why we started this project. There is currently 10 million Americans who have difficulty working. Limited mobility makes day-to-day tasks difficult, and these individuals have to rely on living healthcare assistant. The cost of assisted living is increasing, and there will be a shortage of healthcare assistants. The expected shortage of 808,000 in-home nurses by 2020. This graph shows the expected gap for in-home nurses. So what's the problem? The problem is currently there is no cost-effective system in place that will enable these 10 million individuals to help them perform daily tasks such as object relocation, two-way communication, and remote visual inspection. That's why the system that have these functions is needed. Our solution is to create a robotic assistant for mobility impaired patients, which will have object relocation function, two-way communication function, and visual inspection function. Requirement. Here's the breakdown of our requirement for object relocation, and here is a detail of two-way communication function requirement, and this is a breakdown for remote visual inspection requirement. Our functions include navigation, linear mobility, vertical mobility, two-way communication, storage, and object retrieval function. Now I would like to talk about our design and prototype. So on the left is the prototype we built on the AutoCAD, and on the right is the current status of our robot. So when we are building the robot, we have to decide which material we would like to use for the robot cover, and then we choose between softwood, plastic, aluminum sheet, and steel. Out of these three, aluminum sheet ran the highest in cost, material weight, density. So because of that, we went ahead and used aluminum sheet for our robot cover. And then for the interface control, we choose between wireless controller, Xbox, glove control, and voice control. After weighing the pros and cons, we went ahead with wireless controller. And for the wheel, we choose between dual omni wheel, pneumatic wheel, and magnet wheel. And the specification we consider for this are cost, the weight, load capacity, and material we use. So among all these three, we choose omni wheel because it is very cost effective and it has high load capacity. Now I would like to explain the construction of our prototype. So first, we do the research for the function we will need for the robot, and from this we do the CAD engineering equation and come up with this design. After we come up with the design, we simulate it in AutoCAD to see if this function will be feasible. From that, we verify that our design work. We go ahead and start building the hardware and the software, and we do the programming. The specification for our prototype is the height of the prototype is 0.2 meter and weight 0.7 meter, and the weight is around 19 kilograms and costs $2,000. The brain of the robot is Raspberry Pi, and the programming language we use is Python, and we work on this prototype for roughly 8 months. Here's a detailed breakdown of our mechanical component diagram, and on the right, I highlighted each component of the robot based on the functionality. The maroon color of the component is responsible for two-way communication, which is composed of PC camera and Logitech camera. The PC camera gives the user the wide view, and then the Logitech camera, which is on the arm, gives you the first-person view, which makes it easier for the user when it's trying to grab object with the arm. The highlighted yellow function is the vertical motion function, which is responsible for the up and down motion of the robot arm, which is composed of lead screw and aluminum sheet. We use 8-inch aluminum sheet. And for the linear mobility function, which would be the base of the robot, which is composed of omni wheel and the speed controller. Here is a more detailed breakdown of our electrical component diagram. And on the right, as you can see, I also highlighted the function of the robot, and the maroon color is two-way, the yellow color will be for vertical motion, blue is linear motion, and the red one is graphing motion, which is for the arm. The main power source we use is 12-volt battery, and 12-volt battery connected to the circuit breaker. In case of emergency, something burning, we can shut down the robot right away, and which is also connected to the VRN power distribution panel. Power distribution panel gives power to the device that use higher voltage, and VRN gives power to the device that use lower voltage, which are Raspberry Pi and PWM driver. PWM driver is connected to the motor of our wheel and lead screw, which control the speed of the motor. Our Raspberry Pi is connected to the 2 camera, and it's also connected to the wireless controller. Here's the programming part. First, we set up our motor on individual the port on GPIO. GPIO is a pin number on the Raspberry Pi. And we set up our GPIO as an output, and afterward we set up communication between the GPIO and the motor so that we can control the direction and speed of the wheel. We also program our robot to stop in case there's a communication link between the expert controller and robot lost, so that the robot will be safe and will not move if the communication link is lost. Now I would like to talk about our unit testing. For our unit testing, we have a unit testing for drivetrain, camera, robotic arm, and overall system. The blue highlight indicates the test we currently perform, which is drivetrain testing. For the drivetrain testing, the test cases for this will be linear test and surface test, and for the camera, field of view test, delay test, and quality assurance test. We also have some minor design changes along the process. So on the left is what our design looked like initially, and on the right is what our design looks right now. So the reason we have to do is that after we setting up the wheel, there is a filing issue between the wheel cover and the wheel, and because of that, the robot won't go straight, and then it's really interfere with the speed and the control of the robot. So we decided to cut the cover of the robot, and now it will go straight line, and then won't have filing issue we had before. Then we also have some minor changes in the power supply. First, we use the VRM to supply power to the device that use lower voltage, but initially our Raspberry Pi and 1 PWM drive are burnt out because VRM wasn't functioning as it's supposed to and giving more voltage than it needed. So we replaced it with this small battery pack, and then ever since then we don't have this issue anymore, and it's fixed. I would like to talk about the system testing. For our system testing, the objective is to ensure the robot system can move in linear direction, and we measure the deviation from the center upon stopping. And the procedure include first we mark the origin and the end line and the boundary for how the robot will move, and we use expert controller to pilot the robot, and then we record the deviation. And on the picture on the right show how we do our testing. And then we do the linear testing on the carpet, wood floor, tile. And this graph shows how we are doing the testing. And we use laser pointer to see the deviation, and the person who is doing the testing will record the deviation on each particular floor. This shows our deviation result. The blue one indicates the linear deviation, and the orange indicate linear deviation for wood, and the gray indicate linear deviation for carpet. Here's the breakdown of our business plan. Our model will cost $4,000, and the user will save $7,000 on first year, and on year onward, the user will save $10,000. Our total operation cost will be $485,000. Here's a breakdown for non-recurring costs and recurring costs. This is a diagram showing our optimistic and pessimistic calculation. And here's like the breakdown of our the result for optimistic and pessimistic cost and expected from year 1 to 5. So from the business analysis, we conclude that the break-even will be in 17 months. And at the end of 5th year, our expected gross profit is $6,029,000. And this is a break-even graph. Thank you.